Okay, the symbol equation for the industrial production of ammonia is shown here. And this arrow shows that this is the reversible reaction, reversible arrow, and something here is here, and this negative sign also says something. And although that both the reactants and products are in gaseous state. So name this industrial process. And this is the industrial process for production of ammonia. And the name of the scientist is Haber, who developed this process. So that's why this is called Haber process. State the meaning of delta H. This delta H is actually enthalpy change. Enthalpy change of the reaction. So we should write this is enthalpy change. And this enthalpy change can be negative as here, and it can be positive. Negative means this is exothermic. Exothermic means heat is being released during the reaction. Or in other words, the total chemical energy of nitrogen and hydrogen is more than the total energy of ammonia produced here. That's why uh, sign is, I'm sorry, the total energy of nitrogen and hydrogen is greater as compared to the total energy of this negative sign emphasizes that this is an exothermic reaction, and exothermic reaction means the energy is being released. And if energy is being released, it means product has lesser potential energy as compared to the reactant. So that's why the excess of energy is released. Now in next part, state the typical conditions and name the catalyst used in the industrial production of ammonia. So we should remember that this process occurs around 450 degrees Celsius. So the optimum temperature is 450 °C. And remember that they are asking about temperature and units both. So unit must be written here. And the pressure can be written in either units. It is 200 atmospheric pressure, 200 atm, or you may write it in Pascal or kilopascal. 1 atmosphere is equal to 1 into 10 raised to power 5 Pascal. So it should be 200 into 10 raised to power 5 Pascal. And you remember that Pascal means Pascal, 1 Pascal, it is written PA, is also equal to Newton meter square inverse. And now the catalyst used is iron. You can name the catalyst, or you may write the symbol of the catalyst, any of these. Now the part D, it says state two methods of increasing the rate of reaction. They're asking to increase the rate of reaction. They're not asking for equilibrium shift. Students generally confused about this when they consider that this is related to chemical equilibrium. So they get confused. But remember that what they are asking, so we should answer accordingly. So think about it, what to answer. There are two methods of increasing the rate of this reaction. They have already used the catalyst, so we shouldn't mention it here. Better, it is better. And temperature. Remember that whenever we increase the temperature, although the equilibrium shift can be dependent on the type of the reaction, whether it is exothermic or endothermic, but rate of reaction always increases when temperature increases. So there should be one increase in temperature. So increase in temperature always increase the rate of reaction because more molecules would have energy equal to or greater than energy of activation. So increase in temperature, and another way to increase the rate of reaction is increase in pressure. Why? How it works? So actually, when we increase the pressure, volume decreases and molecules come close to each other. So there would be more chances of collision. So on increasing the pressure, there would be increase in rate of reaction. This is part E. The symbol equation for the reaction can be represented as shown in figure 3.1, that 1 mole of nitrogen reacts with 3 moles of hydrogen to produce 2 moles of ammonia gas. So here we have the bond energy values. For breaking this bond, we need 945 kilojoule per mole energy. So we have 1 mole here. So no problem, it would be used as it is, but it has 3 moles, so it would be multiplied by 3. So then we will get the amount of energy needed to break the bond. So the question is there, use the following steps, calculate the energy needed to break bonds in the reactants. So how much energy is needed to break the bond? And then finally we will calculate the amount of energy. So first, as 1 mole of nitrogen is being broken, so 1 multiplied by 945 and then plus 3 multiplied by 435. So after calculation, we can understand that the total answer would be from calculator 2250 kilojoule per mole. Kilojoule per mole. This is 50, sorry. And this value must be a positive value because bonds are being broken. So we should use this positive sign. Okay, so this is the value. And as we need only energy, so we should write it like this. Energy released when bonds form in the product. For this part of the question, we have two strategies. One is that we can add all the energies for breaking these bonds. These are the nitrogen hydrogen bonds. 3 are here and 3 are here. So then we need the bond energy for at least one of the bond, that is nitrogen and hydrogen, but unfortunately it is not there. But on the other hand, fortunately we have this delta H, that is the enthalpy change. So what can we do? We can use this formula that enthalpy change is equal to the sum of the energies required for bond formation, bond breaking, minus sum of the energies for bond formation. So for bond formation, we need, and we know these two values. This is minus 90, and this is, we have calculated here 22,250 or 2,250. This value is positive, and minus the summation of energy for bond formation. So when it goes there, it becomes, I'm writing here, minus 2250 and minus 90 is equal to minus summation of energies for bond formation. So it becomes 2340, 2340, and as both the side sign is minus, so we can remove this. So our answer would be 2340 kilojoule. So this is one of the way to calculate the bond for energies released for bond formation. Now this is the third part of the question where we have to calculate the energy for an NH bond. So the energy that we have calculated here is the energy released when bonds are formed in the product. And now here we have to see how many bonds are there. 1, 2, 3, 4, 5, 6. So this amount of energy is released, this amount of energy, it is released when 2 moles of ammonia is formed. And 2 moles of ammonia means 6 nitrogen hydrogen bonds. So what would be the energy for single nitrogen hydrogen bond? We can calculate it by dividing this value by 6. So then we will get 6 threes are 18. So 3 would be here, and it becomes 554. 3 nines are 54 and 0. So it would be 390 kilojoule per mole of the energy. This is part F of the question 3. An incomplete symbol equation for the preparation of ammonia in the laboratory is shown. Calcium oxide reacts with ammonium chloride and produces calcium chloride, ammonia gas, and something else here. And what should be that product? Complete the symbol equation. So if you think about it, then you can see here calcium from here and 2 chlorine from here. They are making CaCl2. It's okay. And then 2 moles of ammonia. It means only 2 hydrogens are lesser. So definitely oxygen from here and hydrogen from here combine to form water. So there should be one water molecule. And now you can see this equation is completely balanced. 2 fours are 8, and here 2 threes are 6 plus 2, 8, and everything else is balanced. Now name NH4Cl. NH4, you know, NH4 is ammonium ion, and this is chloride. So the name is ammonium chloride. And now calculate the volume of ammonia measured at room temperature. Room temperature. famous RTP, which forms when 1.12 gram of calcium oxide is heated with excess of ammonium chloride. So this is the balance equation. So we use a stoichiometric method. So first convert the number of moles of calcium oxide. So how can you calculate? MR is already given. So the number of moles can be calculated by dividing this mass by 56. So do your calculation. It is 0. It is 0.02. So 0.02 moles of calcium oxide are there. And we know the ratio of calcium oxide is to ammonia is 1:2. That 1 mole of calcium oxide produces 2 moles of ammonia. So if we have 1.12 moles, so we can calculate the number of moles of ammonia. So X would be 2 times 0.02 moles. I'm sorry, I have written the mass here. It should be number of moles because we have the mole ratio in equation. So the answer is multiply by this, it would be 0.04 mole. And we know that 1 mole ammonia or any gas at RTP produces 24 decimeter cube, or in other words, 24 multiplied by 1000 means 24,000 centimeter cube. So as answer is required in centimeter cube, so I use this relation. So we have 0.04 mole. So volume of ammonia can be calculated by multiplying this value, that is 0.04, with 24,000. So use your calculator for doing this. So it it becomes 960 centimeter cube. Okay, 0.04 times 24. You can do like this even if you are not using calculator. You know this method. So 20 and 20 cancel, it is 240, and here it is 4. 24 fours are 96, 96 and 0, 960. Okay, so this question has been completed now.